We're going to roll into chapter 15, which is about solutions. I think we're getting to the end. We're running out of chapters, so that's good. 15, which is solutions. We're going to talk about really about solubility, the idea of sort of like dissolves like. We'll also talk about concentration units involving solutions. And I think we'll finish up with a little bit of solution stoichiometry as well. So let's get into it here. So solutions are really aqueous solutions. They are the guys that have that aqueous symbol next to them. And really a lot of biological sort of reactions, a lot of chemistry reactions happen in that sort of aqueous environment. And it's really a water environment that we're sort of talking about. A solution is a homogeneous mixture. So as we talked about previously, homogeneous mixtures, right, are something that looks the same throughout. Everything mixes together. Everything looks like one thing. And heterogeneous mixtures that we talked about earlier on, where you do see different phases and stuff like that. So a solution is something that obviously will sort of dissolve and make a substance that looks the same throughout. There's two main parts to a solution. There's the substance that's there in the smaller amount, and that's what's referred to as a solute. And typically speaking, that solute a lot of times is something that is dissolved in the larger part of the solution, which is known as the solvent. And a lot of times, but as we'll talk about, not in all cases, is the solvent water, but water is a very common sort of solvent that's used. It's non-toxic. It works really well, as we'll talk about, for ionic compounds, things that are polar. But you should keep in mind that water is not always the best choice for some things, especially as we'll talk about non-polar things. It's not a very good choice for as well. So if you take both of those things together, you got your solute, you got your solvent, that basically will make your solution. And so, for example, if we take something like water, which is a pure liquid, and we take some sodium chloride, which is a solid, and we put them together, we will make a sodium chloride solution. And in this example here, the sodium chloride would be our solute, and our water here would be our solvent. And it works really well in this case, water, because water, as we know, is a polar molecule. So basically, their negative side by oxygen, hydrogen side more positive. So when we have some type of ion that goes into solution, that's really how it dissolves. The negative side of water basically surrounds the positive ion, which would be the oxygen in the case of water, while our negative ion that goes for a swim will be surrounded by the hydrogen side of water, which will allow it to basically dissolve. The water works really well with something that's ionic. It's able to do really sort of those intermolecular forces. It's basically like an ion dipole sort of situation where they interact really well with one another. How do you know in a solution what the solute is? It's pretty simple. The solute's always the name of the solution. So if you have a sodium chloride solution, the solute should be sodium chloride. If you have like a calcium chloride solution, then the calcium chloride should be the solute. And again, probably if it's ionic, the solvent probably water in most cases, but again, may not always be water, but water again is very common with ionic substances because they work really well together. So because water is polar, it is a very effective solvent for things that really are ionic. It's also very effective for things that are polar. Really, as we'll talk about here in this chapter, most interactions that happen to make something sort of soluble in each other, and again, soluble means that they do mix together, basically revolves around how they're able to interact with each other. So how they're able to use those intermolecular forces and interact with one another. So ions and polar guys could do an ion dipole interaction, and that is basically what we're just talking about, where it could dissolve. Polar and polar things can do dipole-dipole interactions, which means they interact really well with each other. just by, again, the sort of that basic positive side of one is attracted to the negative side of another. So really, for something to be sort of soluble in each other, they have to sort of use the same sort of intermolecular force that they use with themselves. Then they can use it with somebody else that's using the same sort of intermolecular force. So that allows them to interact with each other if they are different sort of substances very well with one another, because they're both coming in with basically the same type of interaction. If you get two things that are really widely different in how they interact with each other, if you have something, for example, that is polar and something that is non-polar, non-polar guys use dispersion forces, which is very, very weak and very different than how polar molecules use dipole interaction. So when they try to come together, they're really not going to be able to sustain an interaction because they're really using different types of sort of interactions to work with one another. So that process where we dissolve an ion in water works really well. It's sometimes referred to as hydration. That also keeps the ions away from each other and allows it to dissolve. When we do dissolve some type of solid in water, we help it along by stirring, right? So as we stir, we're adding energy. We're also adding a bunch of water molecules being thrown all over that solid, and that's going to sort of increase the dissolving of that solid. We know that it is really a physical change when we make a solution, because the solid is really still there, even though we can't visually see it. It's just trapped behind a lot of water molecules, which makes it sort of invisible to us. But we've done this over the semester here in lab. You could take a solution like sodium chloride, and as you heat it, what will happen again is all these water molecules will start to evaporate. And once the water molecules are pretty much out of the way, that's going to allow those two ions, which have a super strong attractive force to one another, which is the electrostatic attraction, to come back together, and you would see the solid reappear. So all those experiments where you took your evaporating dish and you put it up on top of some boiling water and you let it boil off all the water that was in your evaporating dish, you're left with some type of solid residue that's left over. That's really an example of this sort of interaction. Any questions on that there? So here's an example of an ionic solid, and this is how an ionic solid is sort of arranged. It's a very organized, long range, sort of ordered way that comes into a solid. Those are all the ions, which basically try to fit each other together in a way that maximizes the attractive forces between the positive and negative ions and minimize sort of the repulsion forces that would occur when positive guys get near positive guys and negative guys get near negative guys. But as we go to dissolve, we stir, we throw a bunch of these water molecules onto it, and it basically is enough, because there is a lot of water molecules in there, enough to kind of rip apart the ions from each other. And it will start really the dissolving process here, where we have our sort of ion dipole interaction that's sort of happening. The ion being the ion part of that, the dipole being water, which is a polar molecule and has a dipole moment, right? So that's why it has the negative sort of attraction between it. And that process obviously will continue until it sort of fully dissolves. In terms of how things interact with one another, does play a lot about sort of what type of bonds that we see in substances. And just a reminder, hopefully we remember these things. Again, an ionic bond, opposites attract, electrostatic attraction, a result of a metal losing an electron and a non-metal gaining an electron. And that's different than what happens when we have covalent sort of bonding. That is where we have sharing of electron. And as we've talked about previously, that sharing may be equal, which results in a non-polar bond, which essentially has no charge, right? Because you got equal sort of sharing of the electrons. Or results in a polar bond where you do have a partial charge sort of built up on both sides of that bond. One side may be partially more negative and one side may be partially more positive. And that plays a really big role as to how, again, sort of substances can interact with each other, whether or not they have sort of polar bonds. It's a non-polar sort of molecule. So that plays a really big role in sort of how they can interact with one another. And we've talked about that, so we won't go over that again. So let's talk a little about examples of solubility in water. First off, ionic compounds, as we were just seeing in those pictures and talked about, pretty much going to always be sort of soluble in water. The ions will get surrounded by either the positive side of water, which will surround the negative ion, or the negative side of water, which is the oxygen side, will surround the positive ions. But there are some non-ionic substances that are also very soluble in water. Things like sugar and things like ethanol are also very soluble in water. So why are these things sort of soluble in water? If we take a look at ethanol, which looks something like this. So ethanol, which is really like an organic compound here, has a couple of carbons and an OH group. And there's kind of like two parts to this molecule here. Really, this part over here, where we have sort of all the carbons and hydrogens and carbons attached to carbons, that is all non-polar, basically. So that's really a non-polar part of that molecule, is sort of this part of it. But what something like ethanol does have is it does have this bond here on the other end, and that definitely is a polar bond. That is an oxygen and a hydrogen together, difference in electronegativity, going to create this polar bond that we see here, where once again, the oxygen is more negative and the hydrogen is more positive. So because something like ethanol has this OH group there, even though the rest of it is nonpolar, it is able to interact really well with something like water, because water pretty much is the same bond that we see there, which is also negative and positive. So the negative side of one is attracted to the positive side of another, and that allows something like ethanol and water to work really well with one another and mix through what is known as hydrogen bonding. And hydrogen bonding is one of those really strong intermolecular forces between a bond between hydrogen, nitrogen, oxygen, and fluorine, and it allows it to interact really, really well. So something like ethanol would be soluble in water because they have the ability to basically interact with each other the same way that they interact with themselves. So ethanol is able to hydrogen bond with itself. Water is able to hydrogen bond with itself. They're able to then hydrogen to mix and be soluble in each other. Now, solubility does or is impacted by really the size of the molecule and what else is sort of going on there. So even though we may have something like this, say in ethanol, if you take some other alcohols, which is what this is, and for example, if we built out sort of this part of the molecule and put on a bunch more carbons and hydrogens to the back part of the molecule, what we would create is a molecule that now has a much larger non-polar part and just this little part over here that is polar. And what happens with the solubility in those cases is it actually drops tremendously, almost to no solubility. So when you get to like 5 or 6 carbons in a situation like this, even with that OH group, more than those amount of carbons, pretty much you have no solubility in water, because what happens is it's sometimes referred to as steric hindrance, which is basically if you build out this non-polar part really big, pretty much it makes it really hard for water to kind of find this guy over here to interact with. It kind of gets in the way because it's just too big to interact with. Water is a relatively small molecule, so in order to get something to dissolve in water or mix in water, you have to replace the water and water interactions with very similar type of interactions. And as you build out much, much more of the non-polar part here, even that little part that is polar is not going to do a lot in terms of the solubility. So you see a lot of decrease in the solubility of it. Something like sugar, for example, which is a little bit larger of a molecule, but the difference is sugar, as we'll see a picture shortly, pretty much is littered with a bunch of OH groups all over it. So everywhere there's an OH group in something like sugar, it allows it a place to interact with water. And it makes sugar, as we know, right? If you take some sugar and water, right, it will dissolve, right? So they mix really well, and it will be fairly soluble in water. Any questions on that? So here is the solution process. This is not ethanol, but this is your good friend methanol. Might be in the lab. It is able to definitely hydrogen bond with water, as this part is more negative, this part's more positive, works really well again with the negative and positive attraction. Remember that all intermolecular forces and how things interact with each other are really just the basic positive negative attraction, positive thing of one molecule attracted to the negative side of another, and that's ultimately how most substances sort of interact with one another. Here is ethanol, again, doing its hydrogen bonding through that OH group. It's not a super large molecule, so even though it's got a couple of carbons, it's still going to be fairly soluble in water. Now, what about oil and water? Do they mix? And the answer, as you probably know, is no, they really do not mix. And what oil pretty much is nothing more than a super long chain, usually of just carbons attached to carbons. And pretty much, I won't draw all of the hydrogens, but a bunch of hydrogens attached to each of these. I will draw the hydrogens. And it could just kind of keep going on and on and on. And obviously, this really big molecule, which is oil, if you take the electric activity of carbon and hydrogen, is basically going to give you a difference of 0.4, which is a nonpolar bond. So oil is pretty much nonpolar. And because it's nonpolar, what oil wants to use in terms of its intermolecular force is dispersion forces, which is those really weak temporary forces, which is very, very different than what water wants to use. Water wants to use hydrogen bonding, as it is obviously polar here. So water wants to use its negative positive sort of side and do some hydrogen bonding. So when you try to put these two guys together, they are both pretty much coming to the table with different types of intermolecular forces, different types of ways that they interact with each other, to basically maintain that interaction over the long period of time. Now, will they be able to maintain some interaction over a short period of time? The answer is yes, right? Like oil and vinegar salad dressing, you can mix it, right? It kind of mixes, but eventually over a long period of time, everything separates out. Same thing with oil and water, right? You kind of mix it, but eventually all the oil will kind of float to the top, right? And kind of separate out. And that's because everything can use some type of dispersion force for a short period of time. The difference is because oil wants to strictly only use dispersion forces, it will be able to make some interactions break apart, make some interactions break apart. It can't maintain that constant sort of interaction that water is able to do, for example, with another water molecule, able to keep that interaction. And that's because water is polar to begin with. It has a dipole moment. So no matter what happens to water, it always has a positive side, always has a negative side. So it's always good to go in terms of interacting with another sort of polar molecule. Something that's using dispersion forces has to rely on something happening to move its electrons around to kind of make that positive negatives thing. And that means that they can't maintain those interactions over a really long period of time. So that's why oil is insoluble in water. They really don't mix. The other sort of big problem with it is, as I mentioned earlier, in order to get something like oil to sort of mix well with water, you have to replace water and water interactions, which are really small molecules, with these really big sort of molecules that's not really using the same sort of interaction. It just really doesn't fit. It's like, you know, if you try to put like a truck into a garage, maybe you get some of it in, but it really doesn't work very well, right? You can't really get it into the garage. And that's sort of what's happening here. It's just too big of a molecule. It doesn't have the right type of interaction to work well with water, and they obviously will not mix. So that brings up a very common phrase that you hear when you talk about the solubility of substances, and it's the idea of like dissolves like. So things that have the very similar types of intermolecular forces that they use with themselves will be very soluble with others that use the same type of intermolecular forces. So basically what that breaks down to is if we have something that is soluble, which means they will mix. If you have something that's ionic and something that is polar, they will use ion dipole interaction and be fine and soluble with each other. If you have something that is polar and polar, they both will use either hydrogen bonding or dipole interaction with each other, and they will mix. And the one that's sometimes overlooked by people is if you take a non-polar guy and a nonpolar guy, they also will be soluble in each other because they're both using dispersion forces. So even though that's a very weak force, if you put two nonpolar things together, they're both going to be using the same type of weak force. So that's going to allow them to mix really well with each other. You really only run into a little bit of trouble when you kind of cross over and try to put something that's polar and nonpolar together. Those guys will be insoluble, which means they really won't mix. If it's a solid and a liquid, the solid won't dissolve. If it's a liquid and a liquid, they will not mix. By the way, when we talk about liquids and liquids being soluble in each other, sometimes the word miscible is used. Miscible means that two liquids mix together and they basically look like one liquid when it's all said and done. Immiscible is when two liquids really do not mix together and they will basically layer out, and you'll see different layers that basically form. Any questions on that there? So here is a picture of sugar. And again, as you can see, as I mentioned, pretty much there's just OH groups all over the place. So again, even though it is a relatively larger sort of molecule, everywhere where that OH group is going to allow a water molecule to interact very well with it. And again, it increases the solubility. This is pretty much oil down here. And as you can see, it is pretty much just a long chain of carbons and hydrogens, and again, could be in dispersion forces, and a really non-polar sort of molecule. That's where things like gas come from, like octane. You break it apart into smaller chains of carbons and you get, like, you know, gas and other sort of products like that as well. And that is typically what we see when we kind of mix oil and water. Typically the oil or non-polar layer is up on top. The aqueous layer is typically on the bottom, and we have a lot of hydrogen bonding happening here between the water molecules. And again, molecule really has no way to, over a long period of time, maintain any type of interaction with the water molecules that are present. So let's talk about solubility. If something is soluble in another, that basically means that they will mix. So if we take a solute, which is a solid, and it is soluble in the solvent, it is said to be soluble. So salt will dissolve in water. It will do that ion dipole where the ions break apart, water surround them and helps them basically dissolve. If one substance does not dissolve in another, it's said to be insoluble. So as we were talking about there, oil is said to be insoluble in water. There is a limit to the solubility of one substance and another, and temperature plays a really important role in that, especially with solids and liquids. So a lot of times if you increase the temperature, you'll see a greater solubility of a solid in a liquid. That's because when you increase temperature, you're also increasing the energy. So a lot more energy allows everybody to kind of break apart and start the dissolving process. Usually solubility starts to decrease a lot when the temperature comes down. So as you decrease the temperature, a lot less energy, and also decreases the amount, say, of solid that you could get to mix with a liquid at a lower temperature. There are things that are also always sort of soluble in each other. Gases are always soluble in one another because, frankly, gases are flying around, which means because they are flying around, they are constantly mixing with one another as they are flying around in the same container. Liquids are also mutually soluble in each other. So that's going to be your polar and polar liquids are going to mix well. Your nonpolar and nonpolar lies will also mix really well, again, because they're using the same sort of intermolecular forces. So that idea of like dissolves like is really important, and that's the way you could really make a pretty good prediction as to whether or not you would expect something to be soluble in one thing versus another. Two polar things should be soluble in each other. You have two non-polar things, they should be soluble in each other. But if you take a polar and a non-polar thing, you should predict that they should not be soluble in each other. That is why water is a really good solvent, things that are ionic and things that are polar, because they're able to interact well with each other. Water would be a pretty crappy solvent for something that's non-polar, because it's not going to be able to interact really well with one another. As water, again, is going to try the hydrogen bond, the non-polar guy is going to use dispersion forces, so they really will not mix. So again, if you put water in with something that's non-polar, it will not really make it that solid dissolve. The solubility of a solute does depend on temperatures. As I mentioned before, that higher temperature does result usually in a greater solubility, and that lower temperature does result in a larger solubility of a gas in a liquid. Why at a lower temperature is the gas more soluble in a liquid? Because at a lower temperature, if this is my gas molecule should be moving much slower, right? Which means it's going to stay in the liquid part for a much longer time than it was a higher temperature where it would just kind of bounce out of the liquid, right? Because it has a lot more energy. So that lower temperature is going to allow that gas molecule basically to be traveling in the liquid for a much longer period of time, and it would be much more soluble. The solubility of a gas also depends on the pressure. The higher the pressure, the larger the solubility of a gas in a liquid. This is sometimes referred to as Henry's law, which is sometimes the soda can example. In a soda can, before you pop the top, you have your liquid and you basically got some carbon dioxide, which is a gas dissolved in the liquid part. Before you pop the top on the soda can, there's a lot of pressure, right? Which is the sound you hear when you pop the top, right? And because of that, when we have a high pressure, we also have a very small volume, which means the gas molecules are going to be together in that smaller volume. When you decide to drink your soda can, you pop the top and you sometimes see the fizzing come out, right? Fizzing is the CO2 that's escaping your soda can pretty much, right? And that's because you did two things when you popped the top. You released the pressure and you also gave the CO2 an escape route out the top, right? When it goes out the top, the air blows the CO2 away. And what happens when you come back to your soda can after a little while? It tastes a little flat, yeah? And that's because all the CO2 basically just left the soda can. So maybe you still drink it, you don't know. Or you take that first drink and go, ooh, not so good. I don't think I should have done that. So that's supposed to be referred to as Henry's law. So obviously before we pop the top there, much more pressure, keeping that CO2 in the liquid part, which is essentially why it's there, right? To keep your soda tasting a little bit better, right? So when you open it, it still has bubbles, right? And all that kind of stuff. And it tastes like a soda. So let's talk a little bit about solution concentration. There's a few different ways that we could classify solutions. One is a situation where we have too much solute dissolved in a solvent. So there is a point, which is sometimes referred to as the saturation point, where pretty much at a particular temperature, that's as much solid as you're going to get to dissolve in that solvent. So if you're trying to dissolve something in water, there comes a point where you can scoop as much as you want in there, but at some point it's going to stop dissolving. So at that point where you hit where no more of the solute will dissolve, that's what's referred to as a saturated solution. It's pretty much the point where you've hit the maximum amount of solid that will dissolve in that solvent. The opposite case to that is if you are before that point. So before that point is what's referred to as an unsaturated solution, which means you could continue to dissolve more solid. You could actually continue to dissolve more solid in that solvent until you hit a saturated solution. And at that point, you hit a saturated solution, no more of that solid will dissolve. So for example, if we take a little bit of sugar, right, and we put it in some water, it will dissolve. We get the Costco size sugar, right, and we dump it all into that cup of water, it's not going to dissolve, right? It's just going to pile up. That's because at some point, as you're dumping it in there, you're going to saturate that solution and no more of that solid is going to be able to dissolve. Any questions on that? And that really is temperature dependent. So again, the higher the temperature, you could get a lot more of that solid to dissolve. And at a lower temperature, you'll get less of that solid to dissolve. There is another type of solution that we could talk about, which is a supersaturated solution. And a supersaturated solution has basically way too much solid dissolved in it for that temperature in the solvent. at that temperature. So you create a solution that is supersaturated. Basically, you end up with a solution that is still a solution, so still in the liquid state, but you basically have way too much of that solute dissolved in it. How you make a supersaturated solution is typically you make a saturated solution, you kind of get a bunch of solid and you start heating it up. So what happens as I start to heat up my really bad looking test tube there that has some solid and some water in there is, as I increase the temperature, that's going to allow me to dissolve into that water a lot more solid than I could at room temperature. And after you heat it up, you'll have a solution that will look like a solution, obviously. And pretty much at this point, what you typically would do is let it cool back down. So two things are going to happen in this case. As I'm heating it up, I'm getting a lot more solid to dissolve. I'm also probably evaporating off a little bit of the water or the solvent when I'm doing that. As I let this solution then cool back down to, say, room temperature, or a much colder temperature, the solubility of everything I got to down. But it's kind of too late at this point because it's already dissolved in this solution. So what you get is a really unstable solution that is so unstable that, you know, if you just kind of knock it wrong, happened earlier today, you just kind of knock it wrong, it will actually cause all of the solute that's dissolved in there to come out of solution. I'll go like, you have like way too much dissolved in there. Or what you could do is take like one little small speck of whatever you dissolved in there, and you could just drop it into the solution, and that would cause it to kind of tip over the edge, if you will, and it'll go at this temperature too much. And what will happen, it'll go from a solution, and pretty much you can see all of the solid will start to creep out of the solution, and it will go from a liquid state to a rock hard state where you can lift the flask up, dump it upside down, and there's nothing going to come out. It's just like a solid substance that's left up. It's what you do in the lab, perhaps. Yes. And that's basically a supersaturated solution. It's really unstable. Like I said, I've over the years just like touched it, and it just kind of goes and takes all that stuff out of the solution. Any questions on that there? Now, there are some other ways to describe solutions, concentrated and dilute. When we talk about concentration, which we are today as well, the most common concentration is molarity, which is big M, and that is molarity. And you might see it on your bottles. And typically, the higher the number you see next to that M, the more concentrated it is, the stronger of a solution it is. And basically, concentrated solution is a solution that has a relatively large amount of solute dissolved in it. In most cases, we oftentimes don't use concentrated solutions, which are sometimes referred to as stock solutions in lab. We oftentimes will use diluted solutions, which has a relatively small amount of solute in it. The way that we go from a concentrated solution to a dilute solution is we do a dilution, which usually means that we add more solvent. In a lot of cases, that solvent is water. So a lot of times to make a solution more dilute, if appropriate to use water, you could add more water to it, and that will make a dilution. Again, kind of going back to an example that we're all probably familiar with, if you get like the big gulp drink with ice before class and you take some drink, but you leave it in your car until after class, all the ice will melt, right? You come back in and you take a drink of it, doesn't taste as good as it did before because basically all that water from the ice has just diluted down all the syrup and everything else is in there. And it tastes obviously a lot more diluted than it did before, not as strong as the original drink was. So a lot of times we do dilutions, we use things that are much lower molarity than high molarity, but sometimes we do use things that have a very high molarity. Especially if you take 1B, you use things like 18 molar, 16 molar acids and stuff. So it can be relatively strong. All right, so let's talk a little about some concentration units that we use for solutions. The first one is the mass percent. It is also sometimes referred to as the mass percent, abbreviated percent M/M, and that's for mass to mass percent. And to calculate the mass to mass percent, it is the mass of the solute over the mass of the solution times 100%. And really, in this case, the important part of this formula is the bottom number here. And the bottom number, which is the mass of the solute, remember that the mass of the solution. The mass of the solution is really made up of those two things that we talked about, is the solute and the solvent. So you want to make sure that you do get the grams of both of those things and not just the solvent. And the reason I say that is because it is very common in these type of problems that they'll give you that information separate from each other. So they'll give you the mass of the solute separate from the mass of the solvent. And what a lot of people will do is they'll just divide by the mass of the solvent, thinking it's the larger number. So a lot of times you will have to sort of, in these type of problems, add those two numbers together, the solute and the solvent, to make sure that you actually do get the mass of the solution and that you do not divide by, obviously, just the solvent. All right, so let's take a look here at one, perhaps. Why don't you give it a go? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass to mass percent? So calculate the percent mass to mass here. Percent mass to mass here, which is again our mass of our solute divided by the mass of the solution times 100%. In this case, the 2.5 grams of calcium chloride, that is going to be our solute. That is the smaller part of the solution. So the mass of our solute is going to be 2.5 grams. The 50 grams of water is our solvent, and this is a good case for water to be a solvent, as that is an ionic compound, so water will work really well as the solvent. And that means that we have here 50 grams. So we do have the mass of the solute. We do not have the mass of the solution. We do need to add those together again to get to the mass of the solution. So that's going to give us something like 52.5 grams would be our mass of our solution. Now we have the bottom part and everything that we need. So the percent mass to mass in this case, 2.5 grams, which is our solute, divided by not just the solvent, but the total solution times 100%. Grams will cancel, going to give us 4.76%. You could label it M/M, and a little calcium chloride would be good in terms of the answer. Any questions on that there? By the way, when we do have these percent concentrations, we can kind of convert them into conversion factors if we needed to. So since we have this number here, what does this number really mean if we wanted to maybe use it in a calculation? Obviously, we don't need to in this problem. That basically means that if you assume 100 grams of solution, there would be 4.76 grams of calcium chloride in 100 grams of solution. Or if you wanted to use that as a conversion factor and do more of a dimensional analysis approach, you could use it in the opposite way as well. So sometimes you'll come across problems where they do give you the percent composition, not really percent composition, but the percent concentration. And sometimes it's good to kind of convert it into usable conversion factors and do sort of a dimensional analysis approach. You could assume 100 because obviously it keeps the numbers the same. But that's a good way to do that. Any questions on that there? Okay, so let's take a look at one here. Another one. Concentrated hydrochloric acid contains 37.2% by mass hydrochloric acid. What is the mass of HCl contained in 35.5 grams of the concentrated HCl? And by the way, that would be this. Okay, let's take a look. So in this case, we are still dealing with our percent mass to mass, which is our mass of our solute, mass of our solution, times 100%. In this case, we are given the percent mass to mass, which is 37.2%. We are given the mass of the solution, which is 35.5 grams, and we are looking for the mass of the solute. How did I know that this was the mass of the solution and not the mass of the solute? It's very simple, because we are looking for the grams of HCl, and remember that the name of the solution is the solute. So if we're looking for grams of HCl, that means we are looking for the solute. That means the 35.5 would have to be the solution's mass in this particular case. Now you could, because obviously you have the percent, you have the mass of the solution, you could plug and chug into this and just solve for the answer. You could also, again, take a more dimensional analysis approach to it. And when we look at our percentage there, that would mean that we have 37.2 grams of HCl in 100 grams of solution. And that comes obviously from the percentage. Or we could use it as 100 grams of solution divided by 37.2 grams of HCl. So if you took that more dimensional analysis approach, 35.5 grams of solution, we would use the conversion factor here on the left. And that would give us 37.2 grams of HCl over 100 grams of solution. Grams of solution will cancel. 13.2 grams of HCl in this case. Now, that is obviously the exact same answer you should get if you just plugged and chugged into the equation, because it's really the same math, right? So if you put it into the equation, you would have 37.2% equals the mass of the HCl divided by 35.5 grams times 100%. You would divide that and you would multiply that, which is essentially what we did on the other way. So it should obviously come out the exact same. Yeah. You have to show some type of work. Yeah. So the one on the right, you can, that's fine. But you got to show something, obviously, not just the number. Yeah. So like I said, it's basically the same calculation, but you could just set it up however you like, but you do have to set it up one of the two ways probably. Yeah. Other questions? Okay, questions on percent mass to mass. So this is one type of sort of percent concentration. There are actually a couple of other ones that you sometimes come across. So while we're here, let's just talk about those as well. I think I'll just steal the top of this page here. All right, so let's just say there are two other kind of ones that we sometimes come across, and that is percent by volume, percent volume to volume. That is the volume of the solute divided by the volume of solution times 100%. That's like, percent alcohol by volume type of deal. Yeah, so that's basically what that is. There's also percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. It's kind of like density. That's kind of like grams divided by milliliters. The top one is milliliters over milliliters in most cases. These two are ones that you really don't have to worry too much about the bottom one, because usually in those problems, you're sort of just given the volume of solution. It's really just the mass percent one that you have to worry about, making sure you get the actual solution part. But they work the same way. So if you had a 37.2% by volume, whatever this was, HCl solution, that basically means you have 37.2 milliliters of HCl in 100 milliliters of solution. Or you could flip it around and do 100 milliliters of solution contains 37.2 grams of HCl. And same thing if you had a 37.2% mass to volume HCl, that would mean you have 37.2 grams of HCl over 100 milliliters of solution. Or in 100 milliliters of solution, you have 37.2 grams of HCl. So again, all these sort of percent concentrations you can kind of turn into usable conversion factors, and again, take a more dimensional analysis approach. Any questions on any of those there? And obviously, for each of those, you could just plug and chug like we did with the other one. Yeah. Okay, so now that we've talked about these sort of percent concentration units, let's really talk about probably the most common unit of concentration that we use most often, and that is molarity. And molarity is, I would say, probably most of the time when you're doing some type of concentration of a solution, that typically is the unit that you're going to use. So let's talk a little bit about what molarity is here. So molarity is really the moles of the solute over liters of solution, and molarity is abbreviated with a capital M. And that capital M really stands for moles of solute over liters of solution. Most of the time, molarity is just kind of referred to as molarity as moles per liter. You should think of it almost like a formula, like kind of density. We do oftentimes use with solutions molarity to solve for any of those things. So we could use molarity to solve for moles, liters, molarity, all three of those things. So if you want the molarity, obviously it is the moles divided by the liters. If you want the liters, that is the moles divided by the molarity. And lastly, a very common one used a lot is moles is liters times molarity. It is really important, that last one there, if you are using molarity by itself with a volume, that volume needs to be in liters. Otherwise, you're going to be off by a factor of 1,000. It is very common that the volume is given in milliliters. So that milliliters to liters conversion is used a lot. 1,000 milliliters is a liter, and that is used a lot with molarity. It definitely needs to be in liters when you're multiplying it by the molarity. Otherwise, you will not get what you think you're getting. You will not get moles in that case. By the way, when you do calculations, it oftentimes is a good idea to do it more of a dimensional analysis way, and to frankly get rid of the big M, because what most people do when they write big M in their calculation is they have absolutely no clue about the liters part. They actually forget about the liters part. They don't remember there's a volume there. They just think in their head moles, and big M is moles, and that is not correct. So if you have something that is given to you like 4.50 molar sodium chloride, and that's how you say it, you basically, what this means is there's 4.50 moles of sodium chloride in a liter of solution. And that way you can see both of the units, both the moles and the liters, that you hopefully will not forget about it when you're doing a calculation. So I would highly recommend getting rid of the big M when you do calculations. Put both of those units in so that you can see both of those units and you won't forget it. The number always stays with the moles part, and it's always 1 liter. So it's always 1 liter, always stays with the moles part is the number. And you can really use it like a conversion factor as well. If you needed to use it like a conversion factor, you could flip it over as well and put a liter up on top and 4.5 moles of sodium chloride on the bottom. So you can use it like anything else in a dimensional analysis approach as a conversion factor. But again, I would definitely convert those things into moles per liter rather than just a big M. So when we talk about a solution's molarity being, say, 1 molar sodium chloride, what that means is you basically have 1 mole of solid sodium chloride dissolved in enough water to make 1 liter of solution. And we would use water in this case because sodium chloride is ionic. So water would be a good solvent to get it to dissolve in because it's polar. That also means that sometimes you're interested maybe in not the whole thing when we're dealing with an ionic compound, but really in a solution, that ionic compound is not going to stay together, right? It's a strong electrolyte. It's going to actually break apart into the ions. So sometimes when we're dealing with concentrations, we're interested in the individual ions rather than the whole unit. And sort of how molarity works with that is, for example, if we had a sodium chloride solution that had a molarity of 1 molar, when it really is in solution, it really is sodium ions that are floating around. and chloride ions that are floating around. And the way we could relate the concentration of the entire thing to each of the ions is kind of like stoichiometry. So we could see that for every one of these guys, we get one of the sodium ion, which means we would multiply the concentration of the whole thing by 1. And that would tell us that in this solution, there is 1 molar of sodium ions basically floating around. That's the concentration of just the sodium ions. We could do the same thing with the chloride here. For every one of the sodium chloride, there is 1 Cl minus that's going to come into that solution. We would take 1 times the molarity. And that would tell us that in that solution, the chloride ion is also 1 molar. The concentration is not additive, right? 1 to 1 equals 2, not 1. So, but it tells you the proportion basically of each of those ions you get. When this sodium chloride goes for a swim, you get kind of like an equal amount of each of those, right? A 1-to-1 relationship. That means the concentration of each of those are going to be relatively the same in that solution. That is not always the case. So for example, if we had calcium chloride, for example, and it had the same 1 molar concentration, when this breaks apart, we get a calcium ion and we get 2 chloride ions here. In this case, it is a 1-to-1 relationship between the whole thing and the calcium ion, which means that we would multiply again the concentration by 1 molar. And that would give us 1 molar. But when we look at the whole thing to the chloride, it actually is a 1-to-2 relationship, which means in terms of the concentration, we would actually multiply the concentration by 2 in this case. And that would be 2 times 1 molar. And that would give us 2 molar. Once again, that obviously does not add up to 1, but if you just think about logically, for every one of those units that go in there, you get twice as much chlorine, right? As you do sodium, is twice as concentrated, which means the concentration of the Cl minus ions is going to be twice as much as the sodium ions that are floating around there. That is the short version of the calculation, the one I recommend you doing. If it breaks apart into a 1-to-3, you multiply it by 3, 1-to-4, multiply the concentration by 4. The long version, just to show you why it is like that, is you would do like a stoichiometry sort of situation. This would be 1 mole of calcium chloride per liter. It is again a 1-to-2 relationship between these guys. So for every 1 mole of the entire thing, we get 2 moles of just the chloride. Moles of the entire thing cancel, gives us 2 moles of chloride per liter, which is our 2 molar basically. So that's the long version of it. You could very simply multiply it by 2, which is essentially what we're doing there. And obviously, if you did it for the calcium, you would end up with 1 mole of calcium chloride per liter. 1 mole of the whole thing gives us 1 mole of calcium ions. Moles of the whole thing cancel, leaves us with 1 mole of calcium per liter, which is the molarity there and why we multiply by 1 basically in this case. Yeah. So that's really the long version of that calculation, much quicker just to multiply by the coefficient as it breaks apart properly to get the proper concentration. Question on that there. So sometimes you will come across problems where they're not interested again in sort of the whole ionic compound, but just what the concentration of the ions are. A standard solution is one that you make that has a known concentration. You could use molar mass and the moles of your solution to figure out how many grams you would need to weigh out, and you could weigh it out and actually make the solution that you need. All right, let's try one here, a molarity question. Calculate the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters. Potassium is 3910 from the periodic table. And bromine is 79. Okay, let's take a look. So obviously we're looking for the molarity, which is our moles per liter. We want to make 15.6 grams. We don't have the moles, but we do have grams. So we can use molar mass to get us to moles, which is a very common thing that you need to do. In this case, we do have the liters, as it happens to actually be in liters. But as I mentioned earlier, it's very commonly it's in milliliters. So again, very commonly you got to convert those milliliters into liters by using the 1,000 milliliters as a liter. So we do want to focus in here on getting to our moles. So we do need to go to periodic table to get our molar mass. And in this case, we just need to add these together, it looks like. So that will give us 119 grams per mole, which would be our molar mass here of KBr. So taking our grams of KBr, 15.6 grams of KBr, using the molar mass, 119 grams on the bottom, so that cancels per mole. Grams are going to cancel, going to give us 0.131 moles, I believe. Now we do have obviously the top part of what we need. So all we have to do now is put it in. So molarity here would be 0.131 moles divided by our liters. And that's going to give us, we'll call it 0.105. Now the units do not cancel, so you can leave it as moles per liter of KBr. Or if you want at this point, you could go 0.105 big M KBr. So you could kind of give the answer in either way there. Any questions on that particular one there? So again, like I said, a couple of variations in addition to using the molar mass to get to the moles, that milliliters to liters is also very commonly done. Any questions on that one? Okay, let's take a look at one. We're going to skip a couple of the examples, go to, we'll come back to those examples, but we're going to do, I think, this one next. Let's do this example here. We want to know what is the mass in grams of sodium nitrate that's needed to make 2.5 liters of a 0.15 molar solution. So figure out how many grams you need. Sodium is 2299. Nitrogen is 1401. And oxygen is 16. So we want to make the solution and end up with a molarity of 0.15 molar and a total volume of 2.5 liters. So see what you come up with here. Okay, so since we're getting down, let's take a look at this and talk about the approach we should take here. Obviously, we're still dealing with molarity, which is our moles per liter. In this case, we're actually looking for how many grams that we need. We are given the volume here, which is 2.50 liters. It's actually in liters, so we're good on that. We're also given the molarity here of 0.15 molar, which means we have that. So if you're not sure where to begin, that would be a good place to begin, which would mean to solve for the moles. And that's good because we know how to go from moles to grams, right, by using the molar mass from the periodic table. So that's how we're going to basically get there. We could take a more dimensional analysis approach. Again, this guy does mean 0.150 moles per liter, so you can see the units. Or if you needed it the other way around, you could have liters up on top and 0.15 moles on the bottom. So I'm going to take my volume, 2.50 liters. Again, doing it this way, we see all the units. And we get rid of the big M so we don't forget about the liters, so we can see how they cancel each other out. We're going to multiply that. We get 2.5 times 0.150 is 0.375 moles of sodium nitrate is needed. Any questions up to there? Now, I can't really measure out the moles, so we do need to get it to grams. So we're going to need the molar mass there of sodium nitrate. So that's going to be basically 2299 plus 1401 plus 3 times our 16 there. And if we do that, that's going to give us 3 times 16 plus our 1401, going to give us 85 grams per mole as the molar mass. That would be our last step here. We would multiply by the 85 grams up on top, so that we do end up with grams, moles on the bottom, so it cancels. Those cancel out, and we end up with 85 times 0.375, about 31.9 grams of sodium nitrate is needed. So if I were to make this solution, I would go to the scale. I would weigh out about 31.9 grams of my solid sodium nitrate. I would add enough water that I ended up at 2.5 liters. I would give it a mixy, shaky, maybe not so much shaky. And we would end up with a solution there that is 0.15 molar. Any questions on that? That is like identical to the calculation in the lab.